Today's lesson is a bonus section about conic applications. So we're going to take the conics of chapter 11, so the parabola, ellipses, and hyperbolas, and put them more into a context that's more real world, realistic, where they actually kind of end up happening. So we'll just go, we got 3 of these that we'll kind of talk about and go through and show you how to kind of sift through the information. So example 1 says a searchlight has a parabolic reflector. So that means a cross section that forms a bowl, so like a parabola. Okay, and the parabolic bowl is 16 inches wide from rim to rim and 12 inches deep. The filament of the light bulb is located at the focus. Okay, 2 questions. What is the equation of the parabola used for the reflector? And how far from the vertex is the filament of the light bulb? So we want to be able to write the equation. So let's draw a picture to kind of help us describe this. Now, it doesn't matter which way you orient it. You don't even have to be like super descriptive on this. It just said from, and we want to cut these out because they're just a bowl here. So there's our bowl. So from there all the way over there, it says it's 16 inches from rim to rim, and then it's also 12 inches deep. Okay, so using that information, that would give us a point out here. And so now remember, a parabola is a symmetric shape, so halfway in between you'd split that distance of 16 inches. So this point over here would be the point 8, 12. So from halfway to the right it would be 8, from halfway to the left it would be 8 of a value. Okay, and then the y value would be 12 if you're plotting this at the vertex. Okay, so if you're given that point, you can find your equation by starting with your proper general form. So because we're orienting this upwards, we would say x squared is equal to 4py, and then we just need to find our p using our numbers, so we plug in 8 squared and then 4 times p times 12. Okay, so 8 squared would be 64, and 4 times 12 would be 48. So now you can divide both sides by 48. So that gives us a value of 4/3. So now, if you want to write your equation, and we're doing this for A, so go back and plug it in. And so 4 times 4/3 gives us 16/3 times y. Okay, so there's your equation. Letter B now wants to know the distance from the filament of the light bulb to the vertex, so that bottom part. So remember, because of how we're orienting this, we know that the filament's at the focus, and the focus to the vertex is that distance p. And so we already found that, right? So it's a distance of 4/3, so it would be 4/3 inches. Okay? And so that's how you do that problem. Next problem is example 2 says 2 girls are standing in a whispering gallery that is shaped like a semi-elliptical arch. The height of the arch is 30 feet and the width is 100 feet. How far from the center of the room should the whispering dishes be placed so that the girls can whisper to each other? Now, there's a note down here that says the whispering dishes are placed at the foci of an ellipse. Okay. Now, this is one shape that we'll talk about in our next section when we talk about 3D shapes. But if you're looking at a whispering gallery, it's going to be an ellipse kind of shape, but it's like half the ellipse. So you have the foci, or how they say the whispering dishes. There's several places. I think the Jefferson Memorial is an example of a whispering gallery, where there's spots on the floor where if you stand at one spot and somebody else stands at the other spot, then you could talk to each other like having a normal conversation as if they are standing right next to you, which is a neat kind of thing that kind of happens with those kind of structures. But what's happening is because of where you're standing, the sound bounces off of the ellipse, kind of like the distances. You know how the distances of the sun? So that it hits the ellipse shape and then bounces off and heads towards the other foci. So all sound does that, and so as you're talking, it does that in each spot, just because of the angle and the direction. So that's kind of what you're talking about there. So here they say that the height is 30 feet and the length from end to end is 100. Okay, so from there I want to be able to find the center, so, or how far the whispering dishes need to be at the center. So basically they're asking how far are the foci from the center, so you need to find C. So here, if you're given 100 feet, so that's talking about your major axis. The 30 would say that it's just the B value, so half, because you're not going to have the whole ellipse, because you're not going to, it's just going to be, it's at a semi-elliptical arch, okay? So you just have, this is B right there. And then letter A would be half of the 100, because it's 2A, so that gets you 50, okay? So now I can use that to help me find my C by using my Pythagorean theorem. So 50 squared minus 30 squared so then subtracting them gets you 1600, and then square root gets me 40. Okay, so then that means that the distance from the center to the foci, or the whispering dishes, is going to be 40 feet. Okay. Our next example says a comet's path as it approaches the sun can be modeled by one branch of the hyperbola. So y squared over 1096 minus x squared over 41,334 equals 1. So where the sun is at the focus of that part of the hyperbola, each unit of the coordinate plane system is 1,000,000 miles, or 1,000,000 miles. So we want to find the coordinates of the sun, assuming it is at the focus with non-negative coordinates. How close does the comet come to the sun? So here, if you're talking about, so for hyperbola, you have those two shapes. You have your vertices and your foci. So they want to know where the sun is. It said the sun is going to be at the focus. So this is their sun here, and it said in the it wants to assume that the focus is with non-negative coordinates. Okay, so you're just talking about this upper part of the hyperbola, so that's why they use the word branch, because it's just one of the parts of the hyperbola, branches of the hyperbola. Okay, so the comet runs on this path around the sun. So if the sun has coordinates, it'll just be like in the positive. So since you're looking at y squared, it'll be 0 comma something when we're done. But that 0, this comma something represents C. So for C, we need to find you need to find C squared using your A squared and your B squared. So your A squared is at 1096. Your B squared is your 41,334. So then, using your Pythagorean theorem, you add them up. That gives you 42,340. And then square rooting, that gives you 205.99. So then that would be our coordinates. Okay? So that would be the coordinates of a sun on this if our center of the hyperbolas are at 0, 0. So now they want us to be able to find how close does the comet come to the sun. So basically, they want to know what that distance is, because that's the closest the sun and the comet get to each other. Okay, so we need to figure out what this value is. And so since you have A is 1096, then we take the square root of that. That gives me 33.11. Okay? And so the distance between the two would be the sun's distance minus that distance, and that would get us this in-between distance. Okay? So 205.99 minus 33.11 will get us 172.88. Okay? And so that would be 172.88 million miles. Because remember, that's the unit of measurement that they wanted the coordinate plane to be put in. Okay? So these are just a couple examples. We'll have some more worksheets that have more examples on them that you can work out, and we can work those in class if you like. Okay? Have fun.